Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. Level 15 on friction on wedges. A 5-degree wedge is to be forced under a 1,400 pound machine base at A. Knowing that the coefficient of static friction at all surfaces is zero point 0.2, Part A determine the force P required to move the wedge, and Part B indicate whether the machine base will move. So here is the given figure, and remember this wedge is 5-degree wedge. So for our solution, let's have the free body diagram of this machine base, and let's have the reactions, namely NA, which makes 5 degrees with the vertical, and zero point 0.2 of NA, which makes 5 degrees with the horizontal as shown. Then for the angles, 5 degrees, then reactions at B. Then we sum up moments about B equal to 0. So let's begin with the vertical component of NA, which is NA cosine of 5 degrees, then times 70 inches, then minus zero point 0.2 NA times sine of 5 degrees vertical component times 70 inches. The horizontal components, this distance is negligible, so they pass through point B, the horizontal component, so you just have to ignore this distance. The distance, uh, this length is not given, so that means we have to ignore it. Then equals 1,400 times 20, or minus 1,400 times 20 equals 0. From there, we can solve NA. And NA is 408.68 pounds. The total vertical reactions at A and B, or at the underside of the wedge, should be equal to 1,400 pounds. Therefore, from there, we can compute the maximum frictional resistance on the wheelbase or machine base, and that maximum frictional resistance is equal to zero point 0.2 of the total vertical reaction, which is equal to the weight of the machine base. So if this is the free body diagram of the wedge, these are the transmitted reactions forces. Let's call this NA prime. So F max is equal to zero point 0.2 of NA prime plus NB, or this one, if this is NB. But NA prime plus NB is definitely equal to 1,400 because these are vertical upward reactions. It must be equal to this downward weight, or the weight of the machine base. So F max is equal to zero point 0.2 of 1,400, and it is equal to 280 pounds. So that's the maximum frictional resistance. Then we need this in order to state later or indicate later whether this machine base will move. So next we sum up forces vertical, then summation forces horizontal to solve for P. First, vertical. So NA prime minus zero point 0.2 of 408.68 sine of 5 degrees, the vertical component of this friction force, or plus, sorry, plus zero point 0.2 of 408.68, it is upward, so times sine 5 degrees, then minus 408.68 cosine of 5 degrees equals 0. So NA prime is equal to 400 pounds. Then summation forces horizontal equals 0. Then we have P minus zero point 0.2 times 408.68 cosine of 5 degrees. Then minus 408.68 sine of 5 degrees, the component of this force. Then minus zero point 0.2 of NA prime, and NA prime is 400. Then equals 0. So from there we can solve P. P is equal to 197 pounds. And because F max is 280 pounds and P is only 197 pounds, so that means the machine base will be in equilibrium. It will not move. So machine base will not move because P, which is necessary for the wedge to force under the 1,400 pounds, is lesser than that maximum frictional resistance under the machine base. Level 16 on friction on wedges. Determine the smallest horizontal force P required to move the wedge to the right. The coefficient of static friction at all contacting surfaces is mu sub s 0.3. The value of F is 400 newtons and theta is 15 degrees. Neglect the weight of the wedge. So here is the given figure. So for our solution, let's have the free body diagram, normal and maximum frictional resistance, which is zero point 0.2 of N sub C. Because the condition is we have to find P required to move the wedge to the right. So we have impending motion to the right, so frictional resistance should be maximum as shown. So we have the FBD, F is 400 newtons. Then we have the normal reaction and frictional resistance 0.3 of NC as shown. So up to the left for friction, down to the right rather for friction. That's the effect of the force P pushing it. So that when we consider the wedge, P is rightward, so this friction should be opposing leftward. So for the angle, we have 15 degrees NC with the vertical, then 0.3 N sub C makes an angle of 15 degrees with the horizontal. And the reactions at B, because we sum up moments about B equals 0. Considering clockwise moments as positive, so N sub C cosine of 15 degrees times 300 minus vertical component of 0.3 NC is 0.3 N sub C sine of 15 degrees times 300. The horizontal component of N sub C is counterclockwise, and it is N sub C sine of 15 degrees. The moment arm is 20. So times 20, then minus the horizontal component of 0.3 N sub C, which is 0.3 N sub C cosine of 15 degrees times 20. Then minus the moment of the 400 Newton force, which is 400 times 450 equals 0. So solving for N sub C is equal to 704.47 newtons. We then transmit these reactions to the wedge and analyze the wedge through the free body diagram as shown. So we have here N sub C prime plus summation forces vertical N sub C prime plus 0.3 of 704.47 sine of 15 degrees, then minus 704.47 cosine of 15 degrees equals 0. So N sub C prime is equal to 625.77 newtons. Finally, summation forces horizontal equals 0. So P minus 0.3 of 704.47 cosine 15 degrees minus 704.47 sine of 15 degrees, then minus 0.3 of NC, 0.3 of 625.77 equals 0. So from here we can solve for P, and P is equal to 574.2 newtons. Level 17, determine the force P required to force the 10-degree wedge under the 90-kilogram uniform crate which rests against the small stop at A. The coefficient of friction for all surfaces is 0.4. So here is the given figure. So for our solution, let's have to draw the free body diagram of the crate first. And take note that the angle of the wedge is 10 degrees and the incline is also 10 degrees. Therefore, the top of the wedge is horizontal as shown, though the crate makes an angle of 5 degrees with horizontal. So this is the free body diagram. So take note that the top of the wedge is horizontal, so the normal reaction is vertical. Frictional resistance maximum is 0.4 of N1 rightward horizontal. So zero point 0.4 of N1. Then for the weight of the crate, 90 times G, pull of gravity, acceleration due to gravity. These are the component reactions at A. Anyway, we sum up moments about A later. So we have this component which is perpendicular to the edges, top and bottom edges of the wedge. So this is 90G and this is 90G cosine of 5 degrees. So let's superimpose the horizontal and vertical axis. So these components of the weight parallel to the edges of the crate would be 90 cosine of 5 degrees, and this one is 90 sine of 5 degrees. So 90G cosine 5 degrees, 90G sine of 5 degrees. This moment arm of 90G cosine 5 degrees is half of 1.2, so 0.6, while the moment arm of 90G sine 15 degrees is half of 0.7, 0.35. So summation for the moment arms of N1 and 0.4 of N1, let's draw a right triangle here. So this is 1.2 hypotenuse. Since this is 5 degrees, so 1.2 cosine of 5 degrees. And this vertical distance for the moment arm of 0.4 N1 is 1.2 sine of 5 degrees. So summation of moments about A equals 0, clockwise positive. So we have N1 times 1.2 cosine of 5 degrees minus 0.4 of N1 times quantity 1.2 sine of 5 degrees minus 90 times 9.90G or 90 times 9.81 cosine of 5 degrees times 0.6. 90G cosine 5 degrees times 0.6. Then minus 0.6 is half of 1.2. Minus 90G sine of 5 degrees times half of 0.7, 0.35. Then equals 0. From here, we can solve N1. Take note G is 9.81. So N sub 1 is equal to 480.805 newtons. Having found N1, we then draw the free body diagram of the wedge as shown. So for 80.805, 0.4 of 480.805, then we have N1 prime and P inclined. Let's just call this N2. Then maximum frictional resistance is 0.4 of N2. Then we have P. Let's superimpose the tangential and the normal axis so that will be our guide in solving for P. But before that, take note that this angle is 10 degrees, the angle of the wedge. So 10 degrees and 10 degrees. So to solve for N2, we sum up forces normal equals 0. So N sub 2 plus 0.4 of 480.805 sine of 10 degrees component of this force along the normal axis, then minus 480.805 cosine of 10 degrees in this direction, downward direction, equals 0. So N sub 2 is equal to 440.104 newtons. Then finally, to solve for P, this is the tangential axis. Summation forces tangential equals 0. So you have P minus 0.4 over 80.825 cosine of 10 minus 0.4 of N2. 0.4 of 440.104 minus 0.4 of 480.825 cosine of 10 degrees. Then minus 480.825 sine of 10 degrees equals 0. So from there, we can solve for P, and P is equal to 448.9 newtons.